This is 7.1, integration by parts. Here's a formula for integration by parts. It's a little bit complicated to look at it this way. I prefer looking at it this way. It's a little bit easier to remember. You always want to choose u to be the function that's easier to differentiate, or that will reduce a function into a smaller, lower degree. So let's take a look. Let's just dive right into it. So for example, here you have radical x and ln of x. It's going to be easier to differentiate ln x because it's just 1 over x when you differentiate it. So this is going to be our u, and this will be our dv. So let's start with u equals dv equals. So like we said, we don't want to choose dv to be ln x because that's too difficult to integrate, but this is easy to differentiate. So that's why I'm choosing u to be ln of x, which leaves radical x dx for dv. I'm going to change the square root of x to be x to the 1/2, and the dx always goes with the dv. For every problem, the dx always goes with the dv part. All right, then we differentiate this side. So if you differentiate, you're going to get du over dx is 1 over x. But you can multiply both sides of the equation by dx, so that's just going to bring the dx over to the right side. Over here, we're going to integrate both sides. So when you integrate dv, that's just v. And when you integrate this side, you're going to get, you can even put in the integrals if you'd like. The antiderivative will be 2/3 x to the 3/2. All right, and so we've integrated that. And then the formula says it's u times v, so these two, minus the integral of these two. That's how I remember it. U times v minus the integral of v du. So it's going to be u times v minus the integral of this one times this one. I always put the constants in the front. That's just a personal preference of mine, so I'm going to do that. 2/3 integral of 1 over x times x to the 3/2 dx. So that's this times this is all there. And the constant, I moved it to the front of the integral. Then we can simplify this. If you subtract the exponents, you're going to get 1/2. So I'm just going to simplify this to be x to the 1/2. All right, and then this can be integrated. That's not too hard. So our final answer should look something like this. We still have the 2/3, and that's going to be 2/3 if you integrate. 2/3 x to the 3/2. And don't forget the constant of integration is always at the end, plus c, because we're integrating, and there's no limits. So that's why we have to include the constant of integration. Now we can simplify that, and so the final answer will look like this. 2/3 x to the 3/2 ln of x minus 4/9 x to the 3/2 plus c. And that will do it. All right, let's move on to the next problem. All right, this time you have to decide what is u going to be and what is dv going to be. So here, whenever you have like an algebraic expression, that's always going to be u versus the trig function. So this should be our u, because when you differentiate it, the degree gets smaller, which leaves sine beta t dt for our dv. Remember that the differential will always go with the dv. All right, then we differentiate this side. That's easy. That should be du is 2t dt. Notice that I just put the dt. The dt would be down here, but when you multiply both sides, it's going to move to the right side. All right, now we integrate this side. When you integrate dv, you just get v. When you integrate sine, you're going to get negative cosine beta t. But by the chain rule, this is going to leave us with the constant beta, so you have to make sure that beta cancels out, so it's going to be negative 1 over beta. And you can check your answer by differentiating this, and you will get sine beta t. All right, the formula says this times this minus the integral of that times that. So that's going to be negative t squared over beta cosine beta t minus, the formula says minus, but there's a negative here, so it's going to be a double negative, which turns that into a plus integral. There is a constant. The beta is a constant, so I'm going to put the 1 over beta over here. And now we have the integral of t squared cosine beta t dt. Oh, I'm sorry. I was looking at this. It should have been this times this. So let me backtrack. The constant, when you multiply these two, is 2 over 1 beta. So it's going to be 2 over beta. And we still have a t from here times the cosine beta t dt. And notice that here you have another integration by part. So it's a double integration by part problem because you have a algebraic expression times a trig function, which means we have to do this process all over again. Since I've already used u and v, I'm going to change my variables to be capital U and d capital V. So u is going to be t because that's the algebraic expression. dv is going to be the trig expression, and the differential always goes with the dv. Right, so let's repeat this. Differentiate u, you get 1, and the dt moves to the right side. Integrate this side, both sides. If you integrate, you're going to get v equals 1 over beta sine beta t. All right, so that looks good. And now we can go ahead and do this formula once again. U times z minus the integral of those two. So now we're going to have t over beta sine beta t minus the constant comes to the front, integral of sine beta t. All right. And notice that this is all this. So we still have this constant that I will add to the bottom here. So I'm going to drop that constant down right there. All right. All right, the final integral is this, which shouldn't be too hard. So let's see. I might have to open up a new page, or I might be able to squeeze it in. But this will be negative cosine, well, negative 1 over beta cosine beta t. All right, but this is going to be in parentheses, and then we have this constant in the front. So if you consider this, double negative becomes positive. 1 over beta times 1 over beta is going to be plus 1 over beta squared cosine beta t. All right, so it's a lot of terms, so it's a little messy. That's the hard part, is just making sure all your work is organized. So let me let me clean this up a little. All right, we still have to distribute, but remember, this became this. So this term is gone and got replaced with this term over here. So I'm going to write this term first. So our final answer is going to be negative t squared over beta cosine beta t plus, now I'm going to distribute this here. That's going to be 2t over beta squared sine beta t. So that was this times this. And then I got to distribute this over here. And that's going to be 2 over beta cubed. So plus 2 over beta cubed cosine beta t, and don't forget the constant of integration. That will do it. So as you can see, these double integration by part problems can be pretty long and messy, so you just have to make sure that you organize your work so that you don't lose track of all your terms. But that is the correct answer, yes. All right, let's look at our final example. There is one more. Okay. So the difference between those previous two problems and this one has a lower and upper limit of integration, so you have to evaluate. So let's start this one off by always choosing our u and our dv, as we always do. Remember, u should always be the algebraic before the exponential function, because this can reduce in degree, whereas this cannot reduce in degree. So this will be our u. And by default, this will be our dv. Don't forget the differential. All right, if we differentiate, this becomes du 2x dx. If you integrate, this will become v equals negative e to the negative x. The formula says u times v minus the integral of those two. So this would be x squared plus 1 negative e to the negative x minus the integral, but because there's a minus here, minus a negative becomes plus the integral. And I'm going to move the constant out to the front like I always do. X e to the negative x dx. And as you can see here, we have yet another double integration by part problem. So once again, I'm going to resort to a capital U now to be my x, and my capital V, dv, to be my e to the negative x dx. The the differentiation becomes 1, which is just dx. The integral is going to be v equals negative e to the negative x. And then the formula says these two minus these two. So the formula is going to be, don't forget the 2 that's in the front. So I'm going to drop that 2 down there. And then I'm going to write negative x e to the negative x minus the integral of this times this, but the double negative makes that positive, e to the negative x dx. All right. And we can evaluate this pretty easily. So that's going to just be 2 negative e to the negative x minus e to the negative x. End of story there. Distribute. We're going to get negative 2x e to the negative x minus 2e to the negative x. Finally, don't forget to bring that down. So let's bring all that down. So that's going to be negative x squared plus 1 e to the negative x. And finally, we can evaluate by using the lower and upper limits of integration, 0 and 1. All right, so plug in 1 first, and if you do that, you should get, that's going to be negative 2e to the negative 1 minus 2e to the negative 1 minus 2e to the negative 1. That's just plugging in the 1 part to each term. Now I got to plug in the 0. So minus, if you plug in 0, you're going to get negative 1 for the first one, I believe. Let me double check that. 0, 1, negative 1, yes. Minus 0, this is going to be 0 because 0 here is just going to cancel the entire term out. And then if you plug in 0 here, that's going to be minus 2. So this becomes minus negative 3, but minus a negative 3 becomes a plus 3. So this is plus 3. And then these are all like terms. If you combine them, you get negative 6e to the negative 1. And that does it. That is our final answer.